Hello. So today is Friday. Oh my God. Thank God it's Friday. Uh, it's January 29th, so it's almost the end of January, which is kind of good because then we're into February. And by the time February ends, it's March. And then at the end of March, it's April, and it's the springtime. Okay? So here's the thing. Today, this is digital image processing one, and we're going to do a variety of different things. I want to do some talk about optics. Is going to be a very, 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 very high level discussion of optics. But I also, in our you say quest, you might say, to introduce some of these computing techniques. Let me go over the thing. I started to go over the web page last time real fast, but let me do it real fast for some of you. And frankly, what I'm doing isn't going to totally teach you what to do, because the truth of the matter is that for a lot of this stuff you just have to do it yourself. But it at least provides some inspiration and guidance in the right directions to go in. And some of you already know this stuff, and maybe others not. So it's kind of good to just get everybody up to speed. So maybe we could switch over to the computer. So this is my desktop, and let's see. So this is a Mac. So I've installed. Oh, I noticed that there was an update to the compiler this morning, but I hope there won't be any problems. Apple, just okay. Anyway, I installed a thing called on a Mac. It's different on every platform, right? Windows, Linux is probably the easiest, but Mac is, as I said, Unix under the hood. So basically, you don't have to do quite as much. You do have to install a compiler. I think I mentioned that, actually, I'm going to show this in just a minute. This is an application called Term2. The terminal application that you run, shell, in this case a bash shell on a Mac. The default terminal application that comes with the Mac, isn't that great. So most people, it's easy enough to get this piece of free software, and it works better. It's better than just a straight Xterm, because the Xterms you can't cut and paste. I'm not exactly an expert, but the Apple windowing system is, I think, probably based on X Windows, but it's not quite X Windows, so it's their own kind of proprietary implementation. So some of the features like cutting and pasting are a little different. So, and I go to open this thing. So, GitHub. And I go to Grand Labs. Oh, this is the GitHub site. Oh, you can't see this because it's private, but you can see the public web page. So that's the public web page. And I posted some different things here. So help. Thank you, Scott. Scott Dye, for providing some installation pointers. It's best effort kind of a thing. So it's not absolutely guaranteed that everything in here is going to be 100% correct. If you find something that doesn't work or whatever, let us know and we can update it. This is for the Mac OS. There's the Xcode and command line tools you have to install. I just showed you Terminal 2. It defaults to a thing called Z Shell, but I think I did everything in Bash. This is one thing that's sort of fun. The Xcode, Apple is. I love these software companies. How many people have been following the thing with? Yes, I love it. Okay, I won't express my opinion. It's hilarious. Oh, okay. Anyway, yeah. Oh, what was I? Oh, I completely lost my train of thought. It's just so much fun. So I get the Wall Street Journal, so it's really funny to hear them complaining about people being mean to them. Let's see. So Xcode And GCC. Oh yeah. Oh, I know. Apple. Apple. They're wonderful. So they don't use GCC. They have their own compiler called Clang, and what they do is they alias it to GCC. So it's really quite insidious because you have to disable. You have to be careful because you think you're getting GCC, but you're not. Okay, like it's like me pretending I'm somebody else, right? Yeah, so you have to be a little careful about that. And then Homebrew is the package server for installing software packages on the Mac. And yeah, you should get Git. Okay, so now, and then on, okay, but the next thing, oh, in Linux, I don't have any instructions because the Linux people generally tend to be more sophisticated on this sort of thing. And also, the environment is sort of naturally suited, so there shouldn't be as many issues. It should mostly all be there anyway. Then Anaconda. Okay, so what's Anaconda? And you know, um, even just a year ago, I really didn't even understand most of this stuff myself. Okay, so I feel like there must be other people in the same boat. This things have been moving fast. And understanding these things. So what's Anaconda? Anaconda is and you know, I'm not really an expert on this, so some of the things I'm saying may be not exactly correct, but the um, Anaconda is basically sort of manages your environment. It's particularly useful if you're using Python, but it's a little broader than that. And one of the things that you're going to see about Python that's so powerful is that it allows you to install many different packages that can all play nicely together. One of the things that's really, I hate to pick on MATLAB and poor old MathWorks, but one of the things that's a problem with MATLAB is you get pollution in the namespace. So if you bring a lot of packages, they all bang into each other and they don't work together, right? But because Python is a more modern language, they've figured out how to handle that. So you can install all these different packages and use them interactively. So, you know, it's really powerful because it's modular. So you can, you know, bring in one tool to solve one problem, another tool to solve one problem, bring them all together and solve these big, complex, hairy problems. So that's really cool. But then what ends up happening is for every problem you're working on, you have a different configuration you want to use, and it gets really confusing maintaining all the different configurations. So Anaconda is an environment which allows you to manage the packages. So in other words, you can have a different environment for each problem you're working on, and you can install different sets of packages. And one of the things that's important is that you know how like when you're using software, like for instance, recently I was doing some work and I wasn't paying attention, and the little thing come up in the corner on my Mac, and it said, you know, please install the update. And I wasn't. I'm like, yeah. So I hit go, and then I realized I was installing the newest operating system for the Apple, and I'm like, oh no, and of course it was broke everything, and I'm like, but it was too late, you know. So they kind of got me. And so very often people don't want to upgrade to the newest thing because it just breaks everything, right? So, so the beauty of Anaconda is that you can install a particular version of a piece of software package that you know works for your thing and it's stable, okay? And the thing is that with these concepts of Git and commits, we'll see that a commit has a specific hashtag that you know is very long. It's basically generated with a kind of a random number generator. So that identifies that version of the code unambiguously for the indefinite future, you know, until the internet stops existing or something. So you know that you can always get exactly that version and it won't break. So Python handles Anaconda handles that because what it does is it makes sure that the environment has exactly those versions of every software package and that everything works together. So to install Anaconda, so Anaconda is sort of the product name, and then the software is called Conda. But I won't go into the details, but I have links here. So it basically shows you. Oh, this is instructions on how to. That's a. Oh, here's where you get it. Okay, yeah. So they have it for. Oh, hold on. You might have to actually. Okay, I put the link here, but sometimes it doesn't actually go to the right place. You hit download. Oh, here it is. So they have it for Windows, Mac, and Linux. And you just go through the installation instructions, and so we're gonna have that, and then so we have Anaconda. Oh, for some of you that are new to all this, I think I mentioned this before, but there's a difference between an editor for ASCII and an editor for just a Microsoft Word document. They used to call those word processors. So, in the world of point and click, I mean, one of the things I kind of hope to introduce you to is the power of the command line. Okay, the old-fashioned way of doing this still is extraordinarily powerful. I mean, it's nice to have these interactive GUI environments, but the command line is incredibly powerful because it's very modular. You can really do all kinds of very powerful things. So I know it's a little bit scary, but then once you have that power, you're kind of operating at a different level. So you need an ASCII editor, yeah, and I have some recommendations here. There's much better things, I'm sure, but you can. A lot of old guys like me still use VI and Vim. Okay, Vim is just an updated version of VI. The biggest problem with VI is that it gives you carpal tunnel syndrome because you're always hitting, so I have to be really careful. And then a lot of people like to use Sublime. These editors can be designed so that they know the language you're editing, so that way they can help you a lot. And there's this thing called PyCharm, which is kind of interesting. It's a product of this company called JetBrains or something. And hold on, that went to the wrong place. Shoot, I got to update that. Okay, I have a bug in there. But there's actually through Purdue, I think you can get like a commercial version. So that's kind of nice. And if you're good, I mean, it can do all kinds of powerful things that I don't even understand. But anyway, so then, and then this has, what is this? Oh, I have like, so Git, the way you get Git is it's either on your computer already, or if you can use a package manager to install it. I think there's information on how to do that. And GitHub then is this, GitHub would be like, it's the commercial site that implements Git as a repository for you to store your data. And I think actually GitHub is owned by Microsoft now. They bought it recently, which is kind of interesting. And but you can get, I've talked about this, and I've included some cheat sheets that I've made up. So they're not, they could have errors in them or not be perfect, but I just gave you what I use. Okay, so now if I go to if I open the terminal here and I cd into my directory where I've get, and okay, I've already loaded Grad Labs. I guess I could unload it. So I'm just deleting this directory just for fun, so I could be starting from scratch. Then I already have Git installed and I have Anaconda installed. So so I can reload this thing. So I go to, does it have, so if I go to, oh, do I have to remember. So does it have instruction? Actually, as in real time, I'm thinking of bugs I have. So does it say how to clone the Git site? Oh, it occurred to me, something just occurred to me, which is that, can people find this?
It's listed on your website.
Oh, okay, right. I'm getting, yeah, it's not a problem because you don't need to actually download this, okay? What you need to download is okay, so like we go to this image filtering thing, right? So the C code. I guess what I wanted to try to show you was the Anaconda part of it. So hold on. I'll go to the second lab. So I have to keep this straight in my own mind. So in the procedures, it tells you how to do this with Python. So you need to create a conda environment. So so let's say I'm gonna create a, well, first of all, I'll create a directory to work in, I guess. So I'll create a directory called whatever this is. This is called 2D lab, 2D random lab. Make directory 2D rand lab. Okay, I just made that up. Okay. Okay, now what I'm going to do is, so the first thing I have to do is I have to get this stuff. So you need to create this environment. So over here, I'll download this thing called environment.yaml. Here it is. Clear. Okay, and I see I'm using the point and click environment too because sometimes it's more convenient. So there's the directory, 2D RAN lab, and I can copy this over. So I'll drag it over, and then I type ls, and it's there. So if I type more, there it is. You can see the contents. It's just an ASCII file with a really simple structure like that, and that's just the standard structure that that gives the correct commands to conda. So if I type conda minus version, it should okay, so that you can see it's installed there, okay, and it's version 4.9.2. Okay, now you'll have already gone through the process of installing it on your computer so that it's available when you type conda. So, by the way, there's a concept of a path, if you're not familiar with that, which is that it has to know where to look. So I can type which conda, and it'll tell me that's where it found it. So it got installed in there. So that has to be in your path. If it's not, it won't find it, okay? You have to figure that stuff out. It's all useful information because once you learn how to do these things, you'll use it in the future. So right now, I'm in the base version of Conda. So I can go to my Conda cheat sheet. And if I want to list out the environments, I can't remember these commands. So it says here, okay, to list all the Conda environments, I can type that command. So I copy it over here. And you see I have like a bunch of different environments for different projects I'm working on. But now I got to create an environment for this project. Let me make the font a little bigger. So to create a font, to create a project, create a environment for this project, I use this command here, which it tells you what to do in the lab. It's documented in the lab, so you don't. You come over here to the lab procedure. It says it. It says you have to run it. Oh, by the way, if I copy and paste this line here to the command line, it doesn't work. Okay, so don't get worried. I don't know. Did somebody have that experience already or something? Okay, the reason it did is that this dash here isn't the same ASCII character as the true dash. They look the same, but they're different characters. So don't let that throw you. But so I hit return, and it's going to create this environment. It's going to download the various packages. So it downloads NumPy, MATLAB, Matplotlib, and Pillow. Okay, which are the three things you're going to use. You could actually install other packages in Conda environment, and then they'll always be there for future use once you activate that environment. Okay. So it's downloading the stuff over the web and installing it. And now if I go and look at the environments again, you can see now it's got this new environment there. It's called ECE637, okay? And but it's not activated. So then you have to do conda activate ECE637. and now it's activated. And now, okay, I have like this kind of funny script in my environment, which tells me this prompt here gives me information about like what conda environment I have activated here. So it tells me that. You wouldn't necessarily have that. I mean, you could install this, but so you'd have to double check. And the one that's activated is the one with the star in front of it. Also, it tells me what branch I'm in if it's in a Git environment, which I'm not right now. So environments. Now what you see, the stars in front of the 637, which means that environment's activated. So then what I could do is I can create, say, a directory called test, and then I can run this this script here, just as an example. So I can get this data here. Hold on. So I can get this data here, image, and download it and put it in the this directory that I created called test. So this is just a wrong thing. This is just this is a little thing in the Mac windowing system Finder that allows you to look at the directory you're in, because it mostly tries to hide that stuff from you. So I created a subdirectory called test inside of this directory called 2D ran live that I put on my GitHub. It's actually not on Git right now, but then I'm going to download this thing. So that's the Python script. It includes the MATLAB script too, just in case you want it. It's the old MATLAB script, and this was written by. What do I do? Okay. I don't know how to make that bigger, but this was written by Wenry, so thanks, Wenry. And if I come back here and I look at it, okay, so that's a Python script. So I can look at its contents because it's an ASCII file, and that's what it is. I mean, I can also edit it. Now, you guys will probably have your favorite editors for these sorts of things. And I know that there's these environments like Spider, or there's these environments where you can edit the file and then execute it also. But I kind of like the idea of just doing it in this very simple way using command line, because then you really understand what's going on. I mean, I kind of feel like some of those environments hide a lot of stuff from you. Hold on. So maybe I might edit this so these lines aren't so long, but you can see these are ASCII characters that I can display and edit, and there's the various commands. So you can see the structure of the Python file. These are all comment lines. This stuff here, you need this in order to use NumPy and so forth. So this is essentially a script, okay, as opposed to a function. So if you want to run it, and it's kind of hardwired. Maybe it's not. It could be more elegant, but it's hardwired to run on this file image4g.tif. Okay, so you could make it into something nicer. But so if I want to run this, I just type Python, and I give it the name of the file, and it runs it. Should work. If it doesn't work, it'll be very embarrassing. There it goes. It works. Oh gosh, I got lucky. So it did whatever it was supposed to do, which I can't remember what that was. So, but the point is, I wanted to show how you run a Python. And then actually, and that's the power spectral density. I guess that's what it does, that it computes. And then if I hit return or space, I close this, I guess, then it ends the Python script. So you can run Python in a more interactive way like I said, in one of these more sophisticated interactive environments. But I just like the idea that this is like the simplest possible interface. Okay. And then if you wanted to, was you're doing these homeworks, you could create a GitHub account to store your solution. So in case you want to go back to it at some later date, you can. All right. I'm just trying to think. So did I think I went through everything that I wanted to show. Sort of the basics. Right. Good. So is that good? Are there any questions? I think it's probably pretty remedial for a lot of you, but and maybe just I can also tell you this Python version. So you can see that here it's installed version 3.8.5 because it got the newest version of Python. And there's also an old version called Python 2, which was sort of a different branch, but I think that's finally being sort of set aside. And but in the environment file, environment. Hold on. Oh, I'm gonna move up. More environment. In the environment file, it just says NumPy. So usually, not necessarily. I'm not absolutely sure, but typically, if you just say, here it automatically always installs Python, and it typically will get sort of the newest version. But you can specify specific versions. For instance, for NumPy here, I could specify a particular version of NumPy to install. So that's kind of how it works. All right. Are there any questions? So okay, good. So let me get back to maybe we could switch over to the doc cam and we'll go back to the lecture material. And the first lab is due today. Is that correct? Oh, one other question, which is, do people know how to submit their homeworks? They're submitted as PDFs in Brightspace, right? And Wenri, you've distributed the information on the mechanics of how to do that?
Yeah, you can also send out email. I think if they log into the Brightspace, they have an announcement, and it's very, it's like a due date, and there is a homework one.
And there's a way to upload it to it.
Yeah. Yes.
So, okay, so it should be uploadable through Brightspace. If there's any problems, don't panic. That's fine. We're not, we'll get it worked out and we'll make sure, because this is the first time we have submitted things through Brightspace. But Wenri, maybe you and I can also, after class, go over it and just confirm that what the protocol is and make sure that we can send an email out to all the students so that's clear. Okay? But I didn't get like lots of hysterical emails that they didn't know how to submit homework, so I bet it's not too bad. Okay, good. But whenever there's a problem, if there's ever a problem, just contact us, and or particularly CC Wenri because he's probably more responsive than I am. Okay. Okay, now. The modern digital camera, which maybe isn't as modern as this I feel like my modern digital camera here maybe could be more modern. This was modern like a few years ago. I think digital. Are there any like serious or even committed amateur? Committed, I mean that they really like doing it, but maybe photographers in the room. Oh, good. Thank goodness. There's still hope for society. Because I think it's a nice thing, photography. So, are DSLRs still considered like a thing to have, or is it considered just old-fashioned? Oh, okay. So good. So DSLRs aren't obsolete yet. So a digital SLR, single lens reflex camera, is sort of, or at least a few years ago, was sort of the standard of excellence. Now they've come out with cameras which don't have like optics which go directly. Like your cell phone or a conventional consumer camera doesn't have a viewfinder. You basically just look at an LCD panel on the back of it, which displays the image being being captured by the sensor. Okay, and there's some higher end cameras that use that technology, but the traditional technology, which I guess is will probably eventually fade away, is that you have the lenses here, and there's a mirror, and then the mirror reflects the light through a prism and a viewfinder. And so that's it's called a single lens reflex, because there's only, it used to be you had multiple lenses, one for the viewfinder and the second one for the actual imaging. Um, and But now there's a single lens, and you actually look through the actual lens that you're taking the picture. And then it's really, these are mechanical engineering marvels, because at the time you click the shutter, and I have this camera, I own it. Oh no, I own a bit better camera than this. So I'll bring it in for you to see. It's fun to play with. And they're mechanical engineering marvels, because when you press the shutter release, the mirror flips up, and then it has to be a light seal. So it has to be, the design is a little tricky. And there's it used to be, see, these were originally designed for chemical film, okay? And then they were adapted for digital sensors. And so this flips up, and then the aperture, we'll talk about that in a minute, the iris shuts down to the correct diameter that you've selected for the aperture. And then the shutter opens for the fixed amount of time. And the sensor has to actually, the electronic shutter the electronic sensor has to shutter also, and it has to do it in conjunction with the mechanical shutter. But the sound of that mirror flipping into the up position has become like permanently imprinted on the brainstem of society as the sound of a camera taking a picture. Okay, because that's when you take a picture on your like cell phone, sometimes it makes the same sound. I think actually it goes okay, like that classic sound of a picture being taken. That's the sound of this mirror flipping up and down on a DSLR. Okay, so that's kind of cool. But you can play with these cameras; they're fun. I mean, the higher end ones. So the original film was 35 millimeter, and then but making a 35 millimeter sensor is difficult because that's a big chip. Okay, so but a so-called, if you have a DLSR with full frame sensor, so-called full frame sensor, then the sensor is the full size that the film would have, and that has certain advantages in terms of light collection. So, and I have one with a full frame sensor, which is fun. I'm not a very good photographer, but it's fun to own. So, but you can play with it, and you can stop down the lens, and you can see what happens with the different things. So I'll bring that in. That's fine. And ISO, if the ISO is larger, that's a standardized measure of how much light you're collecting. If the ISO is larger, then it means you have, well, it's not the amount of light you're collecting. It's your sensitivity to the light you collect. I'm sorry. So if the ISO is larger, then you can take images in much lower light. So some of these cameras can go up to, 128, yes, so this is 64,000. So they can go to, 12,000 or 24,000 ISO, and which is pretty impressive. When I was young and you had chemical film, if you had really fast film, it was like ISO 400 was really, really fast, and that would be kind of grainy. But now modern cameras, my wife just got a iPhone 12 Pro Max, which is pretty cool. Not iPro, an iPhone 12 Pro Max, and it's got like a cluster of cameras on it. It takes very low light images, so I can't even imagine what the ISO is on it. But anyway, okay, so lens. I kind of hope to go through some Fourier optics, but I don't know if there's going to be enough time. But basically, a lens. Okay, so the idea is that you have this idea of a focal point of lens. So if the light comes in and it's all it's parallel, the light rays are parallel. So that's what would happen if, let's say, you were in space and you were looking at a star. that was very far away. It's essentially a point of light, so that the light waves are coming in, and it's a parallel light rays. So the other way of thinking about it is that the wave front of the electromagnetic wave is a straight vertical line, essentially, coming in like this. Okay, so you want to focus it at a point so that you can focus the star to a point. And so what you do is, the idea is that you've got to slow down the light going here, and you got to speed this light up relatively to that light, so they all meet at this point at the same time. And then you get constructive interference in the wavefront. So this is different. It's important to notice, and it's a complicated issue, that most images, so if you take a picture with your camera, each pixel is measuring photons. So if you have twice as many photons, you have twice as much energy, okay? So photons are like little packets of energy. Whereas, so there's two different ways of thinking of light. One is particle way of looking at it. One is wave, okay? This is the wave way of looking at it. So the waves are electromagnetic waves. So, of course, Maxwell's equations are a little bit complicated. We can't get into all that. But if you can think of it, it's just a sinusoidal signal that modulates the electric field. So the electric field is like the voltage. It's analogous to the voltage. So, so the electric field is this sinusoidal wave if you have only one pure wavelength. So just like one color from a laser. Okay. Now, if you have white light from a light bulb, is many wavelengths. Okay. But if you only have one wavelength, it's just a sinusoidal wave. But what you measure on the sensor isn't the sinusoidal wave. It's the sinusoidal wave squared. It's actually the expected value of the sinusoidal wave squared, because you're measuring the energy, which is the voltage squared. Okay, so those are two very different ways of thinking about it. So when I'm talking about this, I'm talking about the electromagnetic wave, and that in order for that to coherently, the waves to coherently intersect at a single point, which is called the focal point, you need to slow things down here. So it turns out this lens is approximately like a quadratic. Okay, its thickness is a sort of a quadratic function. Okay, and that does the correct quadratic correction to the first order of the path of the light at a single wavelength. A really good high quality lens has to be designed to compensate the focal points at different wavelengths. If it doesn't do it well, you get a thing called chromatic aberration, because some wavelength, the focal length for some wavelengths will be different than others. And that's what happens. Like, what'll happen is that you might have if it's not a good lens, you might have the blue, the focal point for the blue is different than it is for the red. Because red we'll see is a long wavelength, blue is a short wavelength. So you get what's called chromatic aberration. Okay, you'll essentially get rainbows along edges in your images. So, but lens design, modern lens design is very sophisticated. They use computers to design the lenses so that they work well. But the basic idea is that the focal point is the distance that you would have from the imaging surface to the center of the lens, assuming that the things you're imaging are at infinite distance. Okay, in practice, you're usually looking at something that's at finite distance. So then what happens? You have the object distance, and you have the image plane. So this is like where the focal plane array of the imaging device is. And then, so this distance here is this is DO, and this is DI, and DF is a property of the lens. That's the focal length of the lens. So the equation that they have to meet is this, which is that 1 over DF has to equal 1 over DO plus 1 over DI. So essentially what happens is that as the object gets closer, the focal, in order to keep the object in focus, you have to move the focal plane back, or you may have to move the lens out. So, in a camera, what happens is that to focus the camera on the object, you have to move the lens a little bit. So if it's a 50 millimeter lens, then the lens needs to be just a little further than 50 millimeters from the imaging plane in order to keep the object in focus. So you also have this idea of magnification, which is very important. So what happens is that the object is, you're looking at a tree, okay? But the tree isn't the size of a tree on the image. It's a tree, it's like the old joke, in the movies where, I don't know. Well, they do has anybody seen this movie, Elf, around the holidays? It's sort of a Christmas holiday favorite, okay? Like a lot of the scenes in there are shot where what they do is it's a really cheesy effect where they make things look small because the elves have to look small. They have the elves be far away, and then the other objects in the room are close up, okay? It looks really cheesy, but it kind of has a good comic effect. And it's the same idea here, right? So the tree on the imaging plane is really small, right? Obviously on the image, but the tree is really big. So you have the magnification is much less than 1, but it's actually negative because the tree gets flipped upside down, right? But you don't always want to have magnifications less than 1. Sometimes you want to have magnifications more than 1, like in a microscope. So there, what happens is that the sample has to be really close to the lens, and then the imaging plane is far back, so you get a lot of magnification, positive magnification greater than 1. Okay, so right. So it's pretty much that's the deal with that. And then you have an aperture. Okay, so this is all super oversimplified. I mean, you can derive all these things mathematically from first principles using essentially what comes down to signal processing, okay, for the electromagnetic signal. But you have an aperture here. So here's the key idea. Roughly speaking, the lens, or what they call sometimes they call it the pupil plane, okay? So this is the pupil plane. So that's where the lens is. And you have the image plane. That's where the image is formed. Their relationship in terms of the signal is their Fourier transforms of one another, okay? They're not exactly Fourier transforms because it turns out there's this quadratic phase term that's associated with the lens shape, okay? But in the limit, as you go to infinity, it's a Fourier transform. So, and that's sort of what happens with a pinhole camera. So anyway, but you can think of them as being Fourier transform pairs, okay? So, but the difference is that the image you sense at the sensor, you're sensing the energy. So you're actually sensing the square of the signal. Okay? You're squaring the signal because you're measuring the energy, because the energy is the voltage squared. Okay, so they're a Fourier transform pair, and so you have this thing. You have the aperture, and if you make the aperture big, you let a lot of light in. If you make the aperture small, you let just a little bit of light in. So the f-stop, or the f-stop of the lens, which is denoted by n for some reason, is defined as the ratio of the focal length of the lens divided by the diameter of the aperture. So A here has units of length, not area, so as the aperture becomes larger, the n number of the lens gets smaller. So anybody who's a photographer knows if you go to buy a lens, the smaller the n number of the lens, the more expensive it is. So if you have I have a zoom lens, I think. I'm going by memory here. I have a zoom lens. So zoom lenses are harder to make because they have this additional constraint that you have to be able to change the focal length of the lens. But if you have a fixed focal length lens, like a 50 millimeter lens, if there are photographers in the room, I think if the n number is 3, that would be a pretty fast lens, right? If you get 2.5 would be start. At some point, what's a fast lens for a 50 millimeter lens? 2?
1.8.
Oh, 1.8. Whoa, okay, 1.8. So that would be is that an expensive lens?
Nope.
No, it's not. Okay. So, but you could probably get, maybe you could look it up. I can look it up on Google. So as the n number of the lens comes down, particularly if it's a zoom lens or a telephoto lens, the price goes up dramatically, right? So you might get like I don't know, I'm just guessing, say 1.25 or something. You can easily spend $10,000 on a lens, right? At least you used to be able to pretty easily. Well, in some sense, okay, here's an example of a lens you can spend a lot of money on. It's called a telescope, right? So you attach your camera body to a telescope. That's effectively an expensive lens, and so the point is, and those lenses are telescopes are designed to let a lot of light in, so you can see distant objects. Okay, so the n number, as it gets smaller, it means the aperture is bigger. Okay, so now any photographer will tell you, if you're taking a picture, you say, well, why not always make the aperture as big as possible? Well, because there's a problem, and it's called depth of field. Okay, so as you make the aperture bigger, so if you ask a photographer, if you make an aperture bigger, does the image get sharper or blurrier? Excuse me?
It should be blurred, right?
So it's the general intuition, if you talk to a photographer, is they'll say blurrier. What do you say? You're a photographer. There's no right or wrong answer, by the way, so don't feel bad.
It makes anything outside the focal point blurrier.
Yes, it makes anything outside. That's that's much closer to tech. Well, that is technically correct. They're all good answers, okay? So I don't want anybody to feel bad, but that's an excellent answer. It makes anything outside the. So here's what happens, and it's often counterintuitive for people who do photography, is that this is the Fourier transform. So if the object is in focus, in perfect focus, then as the aperture gets larger, the resolution goes up, so the image becomes sharper, okay? Because if you have a larger Fourier, if you take higher frequencies, you get higher resolution spatially, right? And that's why telescopes have huge apertures. Like there's one telescope I was interacting with. I wouldn't say I actually had the data from it because you can't get the data from it. But it's like there's a telescope in Albuquerque that's 3.5 meter mirror. Okay. Oh, mirrors for a real telescope. They don't really make these giant lenses. They make mirrors. It's easier, and there's less issues with chromatic aberration also. So the mirror is 3.5 meters at, like, I don't know, 1 micron, say. So that means that how many wavelengths is that? It has to be precise to 1 micron over 3.5 meters. Whoa, that is a tough mirror to make. Actually, it's made with glass, and then they put a coating of like silver on it or something, an atomic level thickness coating of silver for the reflectance. So a really huge aperture gives you higher resolution. If you want super high resolution for a telescope, right? So, but the disadvantage is if it's out of focus, it's much more sensitive. So the depth of field is related to the depth of field is the range over which the object is in focus. So if you image, so they use this in photography and in like movies all the time, right? Because for various artistic effects, they'll have the background out of focus because it looks more attractive or something like that, or it focuses your attention. And recently, there was like this piece of software, I can't remember, but it was a huge hit. You guys probably have heard of it, that they developed. I think they put it on the Android phones, and it blurs out the background. It basically just segments the image and blurs out the background. And it was like, everybody loved it. What's it called? Do you know? What's it called? Portrait mode. Yeah, it was like a mega hit, and it was like, whoa! I wish I had thought of that. It's so simple, but yeah, yeah. I guess we're running out of time. So depth of field, okay, and this is the equation for depth of field. And I think I don't know. Maybe you guys. But here's the upshot: that you can model a lens as being a linear space invariant filter with the point spread function if you are looking at only the energy. Okay, it's a space invariant filter in both energy and in coherent electric field, but typically we're using it in energy because our cameras are not coherent optical devices. They're non-coherent. They just measure the energy. It's much more sophisticated to build a coherent optical demodulation method. But so that's like a crash course in optics. I think next time I'll just pick up on the tomography stuff. I'll let you finish that up. Maybe we could, and see you later. Bye. I look like.